Huh? It is.
But my job is real life.
Yeah.
Okay, I think we should get started here. We actually don't have a lot to do. We are killing the following questions. The following questions we are not going to do for one reason or another, and we can go over those reasons as well. So the following questions are out.
7.
7 after like having.
Okay, first of all, 7. We already saw that that's
15.
a little bit of a nightmare. It takes a little bit too long to get to the answer. Number 11 is a a name is escaping me. Lagrange error, and as we said before, Lagrange is not going to appear on our test, so not 11. Number 12 is also Lagrange error. Number 14 is also Lagrange error. So that really only gives us a probably a good 10 problems or so to work on. We should be able to get these done pretty quickly, which is good news for you. And now most of these are actually not that bad anymore. So let's take a look at these. So we're starting with number 1. Starting with question 1. And nice, my tablet won't tablet. My tablet's not tableting. Okay, let's try this again. So let's try this question 1 again. Hey, the tablet is tableting. Okay, so we want a radius of convergence. We have this series right here. That n plus 1, n plus 2. Over 4 to the n. And then we x minus pi to the n. And so you look at that and you think, is this or is this not geometric? And it's not geometric. So not geometric, we got to use a ratio test. Actually, let's do this in blue. We have to use a ratio test. Every time you use a ratio test, please write the words ratio test. Even if you mess up, at least someone will know that you're on the right track. So n becomes n plus 1, n plus 1 becomes n plus 2, n plus 2 becomes n plus 3. Denominator becomes 4 to the n plus 1. And then we also get x minus pi to the n plus 1. And we're going to multiply that by our reciprocal, 4 to the n on the numerator, n plus 1, n plus 2. And then be careful here because the reciprocal, you do need to throw this on the denominator, the x minus pi to the n. That does get thrown onto the denominator. We got to be a little bit careful with that. Okay, so we're going to look at cancellation now. Where's my cursor? There we go. So if we cancel things out, we note that the n plus 2 cancels out with the n plus 2 over here. The n plus 1 here cancels out with the n plus 1 over here. The 4 to the n cancels out with all of this 4 to the n. I'm sorry. The 1 cancels out with this 4 to the n. The one here cancels out with all of this. So we're left with very few terms. Oh, yeah, you know, you're right. You're right. Can I delete that? I can delete that. Awesome. Yeah, the n part cancels out. Okay, so what's left over here? Well, clearly I have an absolute value of x minus pi. X minus pi. And then inside the limit, it looks like I have an n plus 3 on the numerator. Yeah, we can take out a 4 as well. We got an n plus 3 on the numerator and an n on the denominator. Okay, this limit, again, I really hate for you to be doing L'Hopital's rule over and over again for these really simple limits. Please figure it out. N plus 3 over n, that simplifies to n over n. That limit is 1. So this limit is 1, giving us x minus pi over 4 needs to be less than 1. Simplified, x minus pi needs to be less than 4. That gives you a center and a radius. Of course, the only thing I'm being asked for is the radius. So the radius is 4. Yeah.
If they did ask for the center, it's pi.
The center would be pi. Center would be pi.
Hmm? If it was x plus pi.
Yeah. Exactly. Okay, any questions with 1? Great. Yeah.
So to get room control.
Yeah. Yes. Okay. Good. Let's move on. Question 2. We want the interval of convergence. Now we have the natural log of x to the n power. And when you look at this one, again, power series, but this is actually geometric. Okay. And one way to see it's geometric is just to write that out. That's 1 plus the natural log of x plus the natural log of x squared plus the natural log of x cubed, et cetera, et cetera. So let's get an interval. We know that the radius or the ratio has to be less than 1. The absolute value of the ratio needs to be less than 1. And so the absolute value of the natural log of x needs to be less than 1. So let's remember a few things. First of all, for the natural log of x, x has to be a positive number. You can't take the natural log of a negative number. If I want this to be less than 1, then I should exponentiate. So e to the natural log of x needs to be less than e to the first power. And so the other thing we're saying is x should be less than e. Wait, something's weird here.
Negative element of x. You do negative x less than x is less than 1, then you get both numbers. You get the whole.
Yeah. That is supposed to be greater than -1, but it's obviously greater than -1, shouldn't it be?
When you say to the negative element of natural log, the x to the negative,
Hang on, well, before we get there, I don't know why I'm questioning this right now, but what I think what we're saying is that the natural log of x should be between -1 and 1. But that obviously makes sense because natural log of x is always greater than 0, right? Anyways, let's just exponentiate from here. E to the -1 should be e to the natural log x should be less than e to the 1. And so that tells me that x should be between 1 over e and e. Yeah.
Let's say the natural log of 0.2 is negative 0.6. Of a negative number.
Oh, x can't be negative, but the natural log can be negative. I'm being dumb. Yeah. Okay. That works fine. So x should be between 1 over e and e. No worries. And that's my interval of convergence. Pause for questions. No questions?
Would there be another case where you have to set it in between -1 and 1?
We're kind of doing it for all of them, but I think for this one, we have to be a little bit more delicate because we are dealing with exponentiation.
Oh.
Okay, that's what's making this one a little bit different. Okay, let's check out 3 then. Check out 3. We have interval of convergence again. We have this series, and hallelujah, this series is geometric. Yeah, sorry.
Because it's not a ratio test, that's why we didn't check for it.
Perfect. Okay, and again, number 3 is not a geometric series. You don't need to use a ratio test. Okay. So again, let's just write down these terms just to make sure. We got a 1 plus x squared minus 4 over 21 plus x squared minus 4 over 21 squared plus x squared minus 4 over 21 cubed plus. So yeah, that is a geometric series. You don't have to fuss with a ratio test. The absolute value of the ratio needs to be less than 1. The absolute value of x squared minus 4 over 21 needs to be less than 1. Let's shove that up here. Absolute value of x squared minus 4 needs to be less than 21. Okay, that's nice. This is a little bit, again, a little bit difficult to do because we are dealing with absolute values here, right? Right. So let's see. This is, no, it's not. What are we doing here? X squared minus 4 should be between 21 and negative 21, right? Right. Add 4 to both sides, we get negative 17. Should be less than x squared, should be less than 25. Okay. And that doesn't really, I mean, x squared is already positive, right? So really this greater than negative 17, that doesn't even matter. All we need to make sure is that x squared is less than 25. Which means the absolute value of x needs to be less than 5. Interval of convergence should be between negative 5 and 5. I'm a little bit nervous. Yeah, okay. Yeah.
So for this problem, is the radius 21 and the center?
Here, just look right at the very end here.
Oh,
Center is 0.
oh, and the radius is 5. Because we up there without imaginary.
This is a very strange problem. Okay.
Well, you just discount the negative, it would be imaginary.
Well, we don't deal with imaginary numbers in this part of calculus. There's a whole other calculus class that deals only with imaginary numbers.
So like since we're not dealing with imaginary numbers, we discount it.
Yeah. You don't have to worry about it at all. Okay. There's literally a whole class on imaginary numbers. Any other questions with 3? Is the solving okay? Okay, let's go on to 4. Now, 4 says determine convergence or divergence. Let's see that series. For 4, we have that n's cubed plus 8 over 3 to the n, 6 to the n. 6 to the n. And we want to know, does this converge or diverge? First of all, not a power series, right? Not a power series. So you're free to use any method you like. You can use nth term test to show that this diverges, although this won't diverge. You could use ratio test if you really wanted to. You could use integral test. You can use a P series. You can use an LCT. I think right here, though, if you notice you have a 6 to the n power, that gets handled really nicely with a ratio test. So I think a ratio test would be the best choice here.
What is direct comparison okay too?
Direct comparison is okay too, but that's kind of seldom used, and I don't know what you directly compare to.
But you compare to 1 over 6
1 over 6 to the n. Well, that's 1 over 6 to the n would be smaller than this series.
But since it's converges.
No, for direct comparison, you need to have a series that's bigger that converges. Okay, so I think ratio test, even though this is not a power series, ratio test is still a powerful series that you can use. So let's take a limit as n approaches infinity. Look at our ratio. We got n plus 1 cubed plus 8, 6 to the n plus 1, 6 to the n on the numerator, and then we got n cubed plus 8. Again, I don't know what this ratio is going to be, so I can't just force it to be less than 1. It's not a power series. I got to deal with it a little bit differently. So we should expand our numerator here. Limit as n approaches infinity. That 1331, n cubed plus 3n squared plus 3n plus 1 plus 9 over 6 times 1 over n cubed plus 8. Again, that's just a quick expansion using the binomial theorem or Pascal's triangle.
Plus,
Yeah, I was thinking ahead. Sorry about that.
Where do you,
Where to get what?
never mind. We're getting that.
Okay. Let's simplify that then. We got a limit as n approaches infinity with that n cubed plus 3n squared plus 3n plus 9. The whole of it on top of 6n cubed plus 48.
why don't we just plug the 6 c and then
You could have. You could have. This limit is 1/6, which is less than 1. Therefore, you have a converging series. Questions with 4. Okay, let's look at 5. That is not what I meant to do.
Wait, so if it's greater than 1, it's diverging.
Yep. Less than 1 converges with the ratio test. All right. N cubed over 3 to the n. Okay, is there a test that we should use here? Well, not a power series, right? Not a power series. So we don't have to use the ratio test. We can use any test we like. It just so happens again that I think the ratio test works really well here. And I'm telling you why that works really well is you have that 6 to the n power. Whenever you have that n as an exponent, the ratio test usually deals with that really efficiently. So let's use a ratio test. Even though it's not a power series, we can still use a ratio test. So we'll take a limit. Was that n plus 1 cubed over 3 to the n plus 1? 3 to the n cubed. Again, you don't have to force it to be less than 1. You just want to know what that limit is. So let's simplify. You get the limit as n approaches infinity. Is that n cubed plus 3n plus 3n plus 1. I think you're going to get 3n cubed. This limit, again, I hate for you to use L'Hopital over and over again here. Just look at the lead terms. N cubed over 3n cubed simplifies to 1/3. This limit is 1/3. 1/3 is less than 1, so we get convergence. Six. Ooh. And number 6, we have, we just got to figure out if this converges or not using a limit comparison test. And the way that we do this is we need to come up with a p-series which behaves similarly to this series. So let's take that general term, 4n over n squared plus 3. Let's take out all the constants. Let's simplify that final ratio. This is the series we're going to compare it to, 1 over n. 1 over n is a p-series that diverges. So we're looking for divergence here. Take a limit as n approaches infinity. Take the original series, shove it on top. Take the p-series, put it on the bottom, and simplify. Four n squared over n squared, that simplifies to 4 over 1. This limit is 4, which is constant, which is a number between 0 and infinity. So since this series converges, or I'm sorry, diverges, this series also diverges. Remember that the limit comparison test says that the two series are going to do the same thing. So if one of the series converges, the other series converges. If one of the series diverges, as is number 6, then the other series in number 6 will also diverge. It's not always converge, it's not always diverge. It's the two will do the same thing. What does this draw with touch? Haven't I been doing that? I didn't need to push a button for that. Questions on 6? Let's take a look at 8. Is this line leaning or is it my imagination?
That's a little up on the right.
That's
What happened? Does that look better? Okay, number 8. We want to figure out the interval of convergence here. Note that it doesn't say open interval, it just says interval of convergence. So we need to test endpoints if we decide to use a ratio test. And guess what? We got to use a ratio test. This is not a geometric series, so ratio test is the appropriate thing to do here. Okay. Limit. N's going to go to infinity. Got x minus 9 to the n plus 1. And I think you're going to 8 plus 2n. This time I kind of want to force it to be less than 1. Although you can hold off on that if you really want to. You don't have to. And how does this simplify? Well, the x minus 9s do simplify, so we're going to get an x minus 9 on the outside here. Always put it in absolute values. And the only thing left here is 6 plus 2n over 8 plus 2n. that limit is 1. Again, look at the lead terms. 2n over 2n simplifies to 1. So we have the absolute value of x minus 9 should be less than 1, giving me a center of 9 and a radius of 1. That'll allow me to write down an interval really quickly. That's going to be from 8 to 10. And that's my open interval. That's not the final interval. It's just an open interval. Now we got to test endpoints. So endpoint test. Let's check our endpoints. The first endpoint is x equals 8. Now at x equals 8, x minus 9 to the n over 6 plus 2n. That's going to turn into negative 1 to the n, 1 over 6 plus 2n. And you're supposed to figure out what is the appropriate test for this series. Yeah, this is alternating, so we're going to use the Leibniz test. Let's take a limit as n approaches infinity of the general term, ignoring the alternating bit. Again, the only question you have to answer is that limit 0 or is that limit not 0? It is 0, therefore convergence. Let's check the other endpoint. The other endpoint was x equals 10. At x equals 10, excuse me, this series becomes 1 over 6 plus 2n, which is close to a p-series, which means I want to use limit comparison.
It should be the series when you plug in 10, it should be 1 to the n.
Yeah.
You like that?
Don't need it.
You don't need it?
1 to the n is always 1.
That's okay.
This is close to 1 over n. Yeah. So we're going to use an LCT. The limit as n approaches infinity of 1 over 6 plus 2n over 1 over n. That's the limit as n approaches infinity of n over 6 plus 2n. Take the lead terms, n over 2n. That simplifies to 1/2, which is a constant between 0 and infinity.
So we don't know.
Nope. Since this series diverges this series diverges. Okay, so now we have our interval. We converge at 8, so we get a bracket at 8. We diverge at 10, so we get a parenthesis at 10. Converge, diverge. Okay. Yeah, sure.
Can you just use the p-tests when you're finding the number 10?
P-test?
The p-series test where you just say the n, the power 10 is equal to 1, so that means it's 10 divergent.
Number 10?
You know, when you're finding 10.
Mhm. Oh, here.
Yeah.
This isn't a P-series.
Is that because of the 6?
The 6 and the 2.
So it has to be by itself.
Yeah. I mean, if it was a P-series, yeah, don't bother with an LCT. But it's not a P-series. Is that straight? Okay, so we're good with number 8. Let's look at number 9. It's like I went out of my way to make number 9 crazy.
Thanks.
I don't know. Not geometric, so you have to use a ratio test. Let's use a ratio test. Limit as n approaches infinity. What is that? X minus 3 to the n plus 1. 3n plus 3 factorial. Three n factorial. I'm going to hold off on making this lesson 1. Let's simplify that. The x minus 3's simplify nicely. And if we're paying attention in class at all, we know exactly what happens there. But the factorials are kind of weird, and I'll go ahead and just do this. 3n factorial, that's not actually that weird. We'll just leave that. But the 3n plus 3 factorial, we can do something with that. So that's 3n plus 3 multiplied by the integer and just before that, which is 3n plus 2. Multiplied by the integer just before that, which is 3n plus 1. Multiplied by the factorial just before that, which is 3n factorial. Notice that the 3n's cancel out, 3n factorials cancel out, and you're left with 1 over this product of binomials. Now, it's not important for you to expand that. If you analyze that, you should be looking at it as a constant numerator and a denominator that's growing. That limit is 0.
Wait, why would you keep the factorial if you expanded out the factorial?
Where?
But when you expanded out the 3n minus 3n plus 3 factorial.
Yeah. Well, this still is the integer in front of 3n, and the integer before that, and the integer before that. So there's a whole bunch of integers being multiplied that we don't want to exactly.
So then why would you keep the factorial sign at the end of the 3n?
Because there's still a 3n factorial there. It's 3n plus 3, plus the integer before that, plus the integer before that, plus the integer before that, plus the integer before that. Keep on going. Okay. Once we get to 3n, we stop writing all the integers because we see that it's going to cancel out with the numerator. So there's no reason to keep writing 3n multiplied by 3n minus 1 multiplied by 3n minus 2.
So and then all the other ones aren't factorial.
Hmm?
And all the other ones, all like the 3 plus 3.
Yeah, those are not factorial.
Those are the ones that like terminate. Like when you like terminate writing out and everything. Like when they don't exploit.
Mhm.
That last one's factorial.
Yeah. And you stop basically when the numerator and the denominator have the same factorial. Okay, from here, this is equal to 0, which is always less than 1. So the series converges for all real numbers. How did I write that here? Oh, just converges, right? Oh no, I wrote it. That's nice. Okay. Any more questions on 9? 9? It is a pun. It's a multilingual pun. Those are the best ones. Same. All right, for 10, we have this, what is that, x minus 6 to the 2n over 16 to the n. This is geometric. This is geometric, folks. That's the appropriate reaction, actually. That's the appropriate reaction. That's the reaction I'm looking for all this time. This is geometric. Is equal to 1 plus x minus 6 squared over 16 plus x minus 6 to the 4th over 16 squared plus x minus 6 to the 6th over 16 cubed. Yeah, that's geometric.
That also is convergence.
So, all we have to do here is look for the cursor. Where's the cursor? There it is. Geometric. So the absolute value of the ratio should be less than 1. The absolute value of x squared, x minus 6 squared over 16 should be less than 1. Why did I write a 6? And perfect. Absolute value, actually we don't need the absolute values. X minus 6 squared needs to be less than 16. That looks like an n. Absolute value of x minus 6 needs to be less than 4. Center is 6. Radius is 4. So x needs to be between 6 minus 4 is 2. 6 plus 4 is 10. Don't bother with the endpoints. It's a geometric ratio. Hey. That's 10. Yeah.
I thought the ratio was because it was 16 to the nth power.
Mm-hmm.
How do you know, like, why wouldn't it be? Like, if you didn't take
If n only appears as a power, only appears as a power, it's going to be geometric. You're welcome. Okay. That takes us to the very last problem. And then we'll open up for questions. Then I'll keep coughing. 13. Okay, so we want error to be, so we have this approximation for cosine. And let's just write that what cosine is. Cosine of x can be approximated by 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. I want to make a couple of observations. And observation 1, cosine x is an alternating series.
Should you write the general term for it?
Not necessary. No matter what value you put in for x, the terms are going to alternate between positive and negative. Do we see that? Okay. So the correct error that we should use is just the unused term. Okay, so the error is going to be equal to, or is going to be less than, the first unused term. Yeah. No?
Oh,
This is 13, yeah? Okay, so what does this question say? This question says we're using cosine of x approximately equal to 1 minus x squared over 2 factorial, which means error should be less than x to the 4th over 4 factorial, which would be the next term in this series because we have an alternating series. So basically, yeah, we want that error. We want the error.
Excuse the interruption, teachers. Clarification. The grades, the 10-week grades are due Thursday 5 p.m. Verification rosters are due Friday morning at 8 a.m. Again, grades are due 5 o'clock on Thursday. And verification rosters are due by 8 a.m.
How many of us are still on campus? He's like making announcements. Like 2 people. Okay.
wow.
Hey, are you gonna see Hatsune Miku?
What?
Are you gonna see Miku?
No.
She's gonna be Miku performing.
Really?
Yeah, in April. Miku. I'm gonna go.
Oh, sorry.
I have to buy, well, because I'm wearing my Miku t-shirt.
Oh, you just realized that.
Yeah. Hey, we're pretty much done here, right?
Oh, that's
No. I mean, we're not done yet, but like we're pretty much done. All we need to make sure is that x to the 4 over 4 factorial is less than 8 over 1,000. So for what values is that true? Well, this is what you can divide by 2. That's 4 over 500, or 2 over 250, or 1 over 125. So x to the 4th over 24 should be less than 1 over 125. So as long as x to the 4th is less than 24 over 125, we're good. Or, if you want to put it another way, as long as the absolute value of x is less than the 4th root of 24 over 125.
Well, I just say like use F3.
We're good.
less
Hmm?
than 1. On the answer sheet, it's just using F, like the third derivative or.
Are you looking at question 13?
Yeah. Yes.
I have absolute value of x is less than 0.6661. You're looking at 11.
I have negative point.
That was before it was changed. We had that problem.
Yeah.
And we had that like somewhere else too. Oh yeah.
So you're at those expressions are all crazy.
Yeah.
Yep.
That is pretty crazy.
Yeah.
So what we did is write. Oh, come on. Come on.
Okay, now you're not going to get a calculator for this. So leaving the fourth root of 24 over 125 is fine. Yeah, that answer guide is wrong.
You feel your pain, Jojo.
Sorry. I'll be sending out a corrected one. Okay. Is there anything you want to go over again?
Go.
Yeah. Mm-hmm.
Like for 15, when it says like write the first 4 terms,
Mm-hmm.
are these non-zero terms? Or?
Yes. Terms should always be interpreted as non-zero terms. Okay. Yeah.
So when it's terms, it's not the power.
Yeah. When you want to refer to the power, you say the degree.
Oh.
Okay. All right, I'm going to stop the recording. Bye.